Hello, my name is Kevin Craig. I have created 12 modules that cover electronics and measurement for mechatronics. Modern engineering practice requires that engineers model, analyze, and predict before they measure. What is mechatronics? The diagram you see I created in 1995 as a professor at Rensselaer Polytechnic Institute. It is now used throughout the world to represent the multidisciplinary field known as mechatronics. Mechatronics is multidisciplinary systems engineering. It is the synergistic integration of physical systems, electronics, controls, and computers through the design process from the very start of the design process. These modules present the fundamentals of electronics and measurement for mechatronics. This is Module 8 on filters. Topics we will cover are an introduction, capacitive reactance, passive filters, low pass, high pass, and band pass, active filters, low pass, high pass, and band pass. Let's first talk about the difference between LTI behavior and non-LTI behavior. LTI stands for linear time invariant. A frequency domain transfer function is limited to describing elements that are linear and time invariant. These are severe restrictions. No real-world system meets them. Linear time invariant system properties are homogeneity. If R of t is an input and C of t is the output, then if you multiply the input by a constant, the output gets multiplied by a constant. Superposition. If R1 is an input to the system and C1 is the response to that input, and then R2 is an input to the system and C2 is the response to that input, then if these two inputs are applied simultaneously, R1 plus R2, then the response, the output, will be the sum of the individual responses, C1 and C2. Finally, time invariance. If an input R produces an output C, then the input delayed by a time T1 will produce an output delayed by the same time. Transfer functions, the basis of classical control theory, require linear time invariant systems, but no real-world system is completely linear time invariant. There are regions of nonlinear operation and often significant parameter variation. Examples of linear behavior include addition, subtraction, scaling by a fixed constant, integration, differentiation, time delay, and sampling. No practical control system is completely linear, and most vary over time. Linear time invariant systems can be represented completely in the frequency domain. Non-linear time invariant systems can have frequency response plots. However, these plots change depending on system operating conditions. Here we see the ideal filter response curves. A low-pass filter will allow frequencies in some low frequency range. A high-pass filter will allow frequencies in a high frequency range. A band-pass filter will allow frequencies in some intermediate frequency range. And lastly, a band-stop filter will eliminate frequencies in some intermediate frequency range. Filters can be divided into two distinct types, active filters and passive filters. Active filters contain amplifying devices to increase signal strength, while passive filters do not contain amplifying devices to strengthen the signal. As there are two passive components within a passive filter design, the output signal has a smaller amplitude than its corresponding input signal. Therefore, passive filters attenuate the signal and have a gain of less than 1. Filters are so named according to the frequency range of signals that they allow to pass through them, while blocking or attenuating the rest. The most used filter designs are low-pass filter. The low-pass filter only allows low-frequency signals from 0 Hz to its cutoff frequency point to pass, while blocking those any higher. High-pass filter. The high-pass filter only allows high-frequency signals from its cutoff frequency point and higher to infinity to pass through, while blocking those any lower. Bandpass filter. The bandpass filter allows signals falling within a certain frequency band set up between 2 points to pass through, while blocking both the lower and higher frequencies either side of this frequency band. Consider a RC low-pass filter, that's resistor capacitor low-pass filter. Here is the RC low-pass filter. We have a voltage in, and the voltage out is measured across the capacitor. This is the low-pass filter at normal frequency. However, the capacitor at DC, or 0 frequency, behaves like an open circuit because its reactance, its impedance, is infinite. So to redraw the circuit at DC, we see that V out is the same as V in, or the supply voltage. At high frequency, what we see is that the reactance, or the impedance, is 0. And so the output voltage then is ground, or 0. These are the limiting values at DC and at very high frequency for the RC low-pass filter. For the CR high-pass filter, the high-pass filter at normal frequency looks like this: a capacitor and a resistor with the output voltage measured across the resistor. At DC, or 0 frequency, because the capacitor has infinite reactance, infinite impedance, we see that the output voltage is essentially 0, ground. At high frequency, because the reactance, the impedance of the capacitor is 0 in the limit, then the output voltage is then whatever the input voltage is at high frequency. So this is the RC low-pass filter, both in normal frequency and then at its limiting values, DC and high frequency. And the same for the CR high-pass filter, for normal frequency and then its limiting values, limiting performance at DC and very high frequency. This is very important to understand because we can often understand complicated circuits by looking at how they perform at very low frequency, or DC, and how they perform at very high frequency by making these limiting simplifications. Capacitive reactance. The circuit shows a AC voltage supply and it's connected to a capacitor. The constitutive equation for a pure and ideal capacitor says that the current flowing in the circuitry around the capacitor, not through the capacitor, is proportional to the time rate of change of the voltage across the capacitor. This is for a pure capacitor, one that has no parasitic resistance or inductance, and it's ideal, meaning linear in behavior. The impedance, which is the ratio of the voltage across the capacitor to the current in the circuitry around the capacitor, is equal to Z sub C. That's how we define the impedance of the capacitor. Another word for the impedance of a capacitor is its reactance, and its reactance is frequency dependent. It's equal to 1 over C times 2 pi f, where f is the frequency in hertz, cycles per second. 2 pi f is omega, which is frequency in radians per second. If I plot reactance versus frequency in hertz, I see that the reactance in ohms at low frequency goes to infinity. At high frequency, the reactance goes to 0. So here's the capacitance. There's a capacitor. There's its reactance, 1 over 2 pi f C. At low frequency, the reactance, as we know, goes to infinity. The capacitor behaves like an open circuit. At high frequency, we see that the capacitive reactance goes to 0, and the capacitor behaves like a short circuit. Here is a passive RC low-pass filter. It consists of a resistor and a capacitor, and we know that the behavior of the capacitive reactance is that at low frequency, it approaches infinity, and at high frequency, it approaches 0. The reactance of a capacitor varies inversely with frequency, while the value of the resistor remains constant as the frequency changes. At low frequencies, the capacitive reactance will be very large compared to the resistive value. This means that the voltage drop across the capacitor, V sub C, will be much larger than the voltage drop developed across the resistor, V sub R. At high frequencies, the reverse is true, with V sub C being small and V sub R being large due to the change in the capacitive reactance value. Let's analyze our pure and ideal RC low-pass filter. We have an input voltage, pure and ideal resistor, pure and ideal capacitor, and we assume that there is no circuit connected to my RC low-pass filter, so I out equals 0. We want a relationship between the output voltage, which is the voltage across the capacitor, to the input voltage. We know that for a resistor, the voltage drop across the resistor divided by the resistance will give me the current flowing through the resistor, or in this case, E in minus E out equals I through the resistor times R. And IR through the resistor and IC through the capacitor are the same, and we just call it I. For the capacitor, the current is proportional to the time rate of change of the voltage across the capacitor. These are my constitutive equations for the pure and ideal resistor and capacitor. If I apply Kirchhoff's current law to this node, the current going into the node I sub R equals the current going through the capacitor I sub C plus I out. But I assume I out is 0, and in doing so, I assume there's nothing connected here, so there's no loading of this RC low-pass filter. So IR equals IC. IR we know is E in minus E out over R. IC is equal to C times the time rate of change of the voltage across the capacitor, which is E out. If I combine these, I get what we identify as a first order, linear, constant coefficient, ordinary differential equation. We define RC as the time constant tau, and in general form, we have a constant times E in this case it is 1. So the general form for this first order, linear, constant coefficient, ordinary differential equation is tau times the time derivative of E out plus E out equals K times E in. A preferred approach to obtaining the differential equation by first obtaining the transfer function is to use the concept of impedance and the voltage divider. Impedance is voltage over current. For a resistor, voltage over current is the resistance. For a capacitor, voltage over current is 1 over CD, where D is the differential operator. When we use D to represent the derivative, we are then moving from the domain of differential equations to the domain of algebra. So everything that follows now is algebra. If I solve for E out over E in using my voltage divider equation, E out is equal to 1 over CD divided by R plus 1 over CD times E in. So E out over E in equals 1 over CD over the sum of R plus 1 over CD, which if I simplify algebraically, I get 1 over RCD plus 1, which I call my transfer function. It's in terms of the differential operator, and the differential operator is algebraic. If I now cross multiply RCD plus 1 times E out equals E in times 1, and then I distribute the E out, RCD times E out plus 1 times E out equals 1 times E in, and then I use the differential operator and express it as d dt, I have RC dE out dt plus E out equals E in, which is the first order constant coefficient linear ordinary differential equation. I obtained it by first obtaining the transfer function and then obtaining the differential equation from that transfer function. I can also go backwards and get the transfer function from the differential equation. Frequency response. Frequency response is defined as the steady state response of the system, any linear system, to an input sine wave at a particular frequency. Here we're talking about our first order system, our first order linear constant coefficient ordinary differential equation. If the input is a sine wave with an amplitude and a frequency, then the output at steady state, after all the transients have died away, will be a sine wave, same frequency, but the amplitude will be a function of frequency, and there will be a phase angle that's a function of frequency. So the output in the steady state is some C2, a function of frequency, times A, which is the input amplitude, times the sine wave of the same frequency, plus a phase angle, which is a function of frequency. The tangent of that phase angle is minus tau times omega, where tau is the time constant in my differential equation. And C2, the amplitude, is K from my differential equation, divided by the square root of 1 plus tau squared times omega squared, where omega is the frequency in question in radians per second. So the complementary solution will decay to 0 with time. That's what we mean by the transient response. The particular solution is the steady state solution. The input is a sine wave, and the steady state output is a sine wave with the same frequency, but with a frequency-dependent amplitude and a frequency-dependent phase angle. Here we see the frequency response of a first-order RC low-pass filter. It consists of two graphs. The graphs are called the frequency response plots or the Bode plots. They show the amplitude ratio, output over input, versus frequency in the steady state. In the steady state, the output will be a sine wave, same frequency as the input sine wave, but the amplitude ratio will depend on the frequency. Over a range of frequencies called the bandwidth, the amplitude ratio is almost 1, 0 dB. At higher frequencies beyond the bandwidth, the amplitude ratio drops off with a constant slope of minus 20 decibels dB per decade, where a decade is a 10-to-1 frequency change. The bandwidth is defined by the point f sub c, which is the cutoff frequency. It's the frequency at which the amplitude ratio drops minus 3 dB, or 0.707, of the low frequency value. I know for a first order RC low pass filter, the time constant is R times C, and the cutoff frequency f sub c is 1 over tau radians per second, which I multiply by 1 over 2 pi to convert it to hertz. So this point right here is 1 over 2 pi times tau. If I look at the graph now for phase angle versus frequency, at low frequency, the input sine wave and the steady state output sine wave are in phase, 0 degrees. The phase difference starts to occur immediately as the frequency increases. And at the breakpoint, f sub c, the frequency is minus 45 degrees, which means that the output sine wave lags the input sine wave by 45 degrees. It's exactly 45 degrees, minus 45 degrees, at the breakpoint. At high frequency, the phase angle will approach minus 90 degrees as the frequency increases higher and higher. So these two plots are the Bode plots for a first order RC low pass filter. The key characteristics are that the bandwidth, the cutoff frequency, is defined by 1 over tau times 1 over 2 pi, which gives me the cutoff frequency in hertz. At that frequency, the amplitude ratio drops minus 3 dB, or 0.707 of its low frequency value, and the phase angle at that breakpoint is minus 45 degrees. Below that breakpoint, the amplitude ratio is flat, and the phase angle varies from 0 degrees to minus 45 degrees at the breakpoint. At high frequencies, the slope of the magnitude plot is a straight line with a slope of minus 20 dB per decade, where a decade is a 10-to-1 frequency change. And the phase angle proceeds from minus 45 degrees to minus 90 degrees asymptotically. I can create a second order low pass filter by simply connecting two first order RC low pass filters together in series. Can I assume that the behavior of these two RC circuits in series is simply the product of their individual ideal performances? The answer is absolutely not. The reason is that when I analyze a single RC low-pass filter, I assume that it is unloaded, that the current flowing out of the RC circuit is 0. Clearly, for the upstage RC filter, there is current leaving the first stage and flowing into the second stage. The first stage is loaded. The second stage, if there is nothing connected to it, the output current will be 0, and this then behaves as an unloaded RC low-pass filter. What does this mean? It means that for the downstream stage, we can use our ideal unloaded transfer function, which we will call G2 of S. Remember, S is just our differential operator. However, the upstream stage, its transfer function needs to be modified. And the modifying factor is as follows. G1 is the ideal unloaded RC low-pass filter transfer function. The modifying factor is 1 over 1 plus the output impedance of the upstage component, upstage filter, divided by the input impedance of the downstage filter. And we see that if this ratio, output impedance of G1 divided by input impedance of G2, is much, much smaller than 1, then V out over V in approaches then the ideal G1 times G2. This is exact. This will give us the exact input-output relationship. Why is this important? It's important because input and output impedances of electrical systems can be measured. And if they can be measured, then when they are connected to other components, other systems, the nature of their connection, their behavior once they're connected, can be predicted exactly. Let's look at this a little more closely. Here is our RC low-pass filter. It's passive, right? There's no op amps in our filter. It's a resistor, a capacitor, and we have 2 ports, an input port, voltage and current, product is power. An out port, voltage and current, product is power. In order to completely describe this behavior, we must relate the input variables, voltage and current, to the output variables, voltage and current. I do that here using my Kirchhoff's current law at this node. It says that I in plus I out, because I have I out going into the node, minus the current flowing through the capacitor, which is C times the time rate of change of the voltage across the capacitor, that must equal 0. So this then is Kirchhoff's current law for this node. And rewriting it using my differential operator, S or D, I get this algebraic equation. Kirchhoff's voltage law says the sum of the voltages around this closed circuit must equal 0. So I have E in minus the voltage drop across the resistor, which is I in times R, minus the voltage drop across the capacitor, which is E out. That must equal 0. So I have E in equals E out plus R times I in. If I combine these 2 equations, I can write them in matrix form. In matrix form, this says E in equals RCS plus 1 times E out minus R times I out. I in equals CS times E out minus 1 times I out. Now, if I assume that I out is 0, I can come here and just make this 0. And if I do that, I get my ideal transfer function. E out over E in equals 1 over RCS plus 1, which we call G, the ideal transfer function. It's very important that we look at the complete description that relates the variables at the input whose product is power to the variables at the output whose product is power. Then we have a complete description of this RC low-pass filter. Well, if I now connect an RC low-pass filter to an identical RC low-pass filter, and even though the output of the second RC low-pass filter I assume to be 0, meaning there's nothing connected to it, it's unloaded, is the transfer function between the output and the input simply 1 over RCS plus 1 squared? The answer is absolutely not, because right here, there is current flowing from the upstream RC circuit to the downstream RC circuit. So if I derive the overall transfer function for this RC circuit from first principles, I will redraw it to facilitate analysis. So here I have my R and my C for the upstream, and here's the R and the C for the downstream. I know that E out is the voltage measured across this capacitor here. So, and I identify this node A because I need that for my analysis. So I can say that E out over E in equals E out over EA times EA over E in. And that's my relationship here. E out over EA using my voltage divider, which is permissible because there is no current flowing out of the second RC circuit. E out over EA is this impedance of the capacitor divided by the sum of the impedance of R and the impedance of the capacitor, summed together, or 1 over CS over R plus 1 over CS over 1 over RCS plus 1. Remember again, S is the differential operator D. Now, I can then look at R and C and say they're both in series. Impedances in series add. So Z1 is what I have closed here in the dashed box, and it's the sum of R and C in series, which I simplify here. Then I recognize that Z1 and this C are in parallel, and resistances in parallel, or impedances in parallel, the equivalent impedance is given by the product over the sum. That's only true for two impedances in parallel. And if I simplify that, I get this relationship. Then I can use my voltage divider and say EA over EN is equal to Z2 divided by R plus Z2. And I work through the algebra here. Once I have that, I have EA over EN, which is what I need here. I already have E out over EA, which is right here. If I combine these now, I get E out over EN, and I see that it's equal to this expression, which is not 1 over RCS plus 1 squared, but has this additional term. And the answer why, it's because the downstream component loads the upstream component. Now I can find this out, get the same result, two additional ways. I can simply take my matrix representation, complete representation, relating input variables to output variables. Remember, the product is power. So this is voltage and current at the input to the upstage component, the upstage filter. This is the output voltage and current for the upstage RC filter. This is the input voltage and current for the downstream RC filter. This is the voltage and current output for the downstream RC filter, since I recognize that E out 1 equals E in 2, I out 1 equals minus I in 2, just by the sign convention I've used. If I then multiply these two matrices together, I get this result. And I find that since I out 2 is 0, because nothing is connected to the downstream RC low-pass filter, and I simplify and solve for E out 2 over E in 1, I get the same result. Similarly, I know that E out 2 over E in 1 in terms of impedances is the ideal transfer function for the upstream component times this factor, 1 over 1 plus the output impedance of the upstream divided by the input impedance of the downstream times the ideal transfer function for the second RC low-pass filter. The output impedance of an RC filter is the output voltage over the output current with the input voltage set to 0. If you solve for that, you get this result. The input impedance is the input voltage divided by the input current with the output current set to 0. If you solve for that, you get this result. If you plug these two results into this ratio, you get the same result. So here are three different ways you can identify the overall input-output relationship for an RC circuit, either from first principles or by using the complete matrix description of each RC circuit and combining them mathematically through matrix multiplication, or lastly, by using input and output impedances. One way to prevent loading is to insert between the upstream stage and the downstream stage what we call a unity gain buffer op-amp. This buffer op-amp has unity gain, has an input impedance ideally that is infinite, an output impedance that ideally is 0, and it prevents the downstream component from loading the upstream component. So now the overall transfer function, V out over V in, is the ideal upstream transfer function for this RC filter times the ideal transfer function for the downstream RC filter, the second stage, because we have inserted a unity gain buffer op-amp. Let me show you in hardware how we can test this. Here I've breadboarded a RC second order low pass filter, and I've hooked it up to my MyDAC, my National Instruments MyDAC data acquisition device, and hooked it up in a way to view the Bode plot, the frequency response plot for this RC second order low pass filter. And if I do that, I see that I have here my second order RC low pass filter. And I notice that I still get a flat response at low frequency, a slope now that is minus 40 dB per decade, because I have two RC low pass filters, a phase angle that goes from 0 degrees and will approach minus 180 degrees at high frequency. So here's how I can measure that frequency response plot in hardware using my National Instruments MyDAC. And the breakpoint for this is the frequency at which the amplitude ratio drops minus 3 dB from the low frequency value, which is 0. So at minus 3 dB, which I see right here, the phase angle is minus 51.33 degrees, and the frequency is 28.84 hertz. Now, if I put a buffer in between the two RC low-pass filters. So here I have one RC low-pass filter. Here's the other RC low-pass filter. And I have my unity gain buffer op amp. The unity gain buffer op amp ideally has infinite input impedance, zero output impedance, and will prevent the downstream RC circuit from loading the upstream RC circuit. I want to determine the Bode plot, the frequency response plot, and I make the connections just as I did previously. And the result is my Bode plot here. I still see at low frequency my horizontal 0 dB, at high frequency minus 40 dB per decade, at low frequency the phase angle approaches 0 degrees, at high frequency it will approach minus 180 degrees as the frequency is increased, and the minus 3 dB point is at now a different frequency. It's at a higher frequency, 47.86 hertz, and the phase angle is different than the RC-RC circuit. And I've noted that right here. The point we should make is that in both cases, we can predict the response that we will measure from the analysis that we did. So as I've emphasized all along, we need to model, analyze, and predict before we measure, so that when we measure, we can determine if our measurements are correct and they agree with our analysis. Here's a general diagram of the frequency response of that second order low pass filter, the RC-RC circuit in series. And we see that for an RC circuit by itself, at high frequency, the slope is minus 20 dB per decade. For the RC-RC circuit, minus 40 dB per decade. And we see that the breakpoints, the frequency at which the amplitude ratio drops minus 3 dB, or 0.707 of the low frequency value, which is 0 dB or 1, because we can't have amplification here. And we see that that breakpoint is different. And we notice that in our two experimental plots from the MIDAC. We notice that difference. In practice, we've already seen cascading passive filters together to produce larger order filters is difficult to implement accurately, as the dynamic impedance of each filter order affects its neighboring network. What we're saying there is that the downstream RC circuit loads the upstream RC circuit. We can reduce that, we've seen, by adding a unity gain buffer op amp. But you can also reduce this loading effect by making the impedance of each following stage 10 times the previous stage. So in this case, R2 should be 10 times R1, and C2 should be 1/10 of C1. Second order and above filter networks are generally used in the feedback circuits of op amps, making what are commonly known as active filters. So we usually create higher order filters by making them active with op amps. I've now created in MATLAB two Bode plots and laid one on top of the other. The first is for our first order RC filter. To make things simple, I've made tau equal to 1. I know the transfer function is 1 over tau s plus 1. And here's the Bode plot. It's flat at low frequency at 0 dB, minus 20 dB per decade at high frequency, and the breakpoint, where it's minus 3 dB, is at a frequency of 1 over tau, which is 1, which is 10 to the 0 radians per second. For the second order filter, and I noticed that at that frequency, 1 radian per second, the phase angle is minus 45 degrees, as we predict. For the RC-RC circuit, the transfer function is given by this expression. If I ask MATLAB to give me the Bode plot for this transfer function, I see that at low frequency, it's 0 dB, it's flat. At high frequency, it's now minus 40 dB per decade. But I notice that the breakpoint at minus 3 dB is at a frequency of 0.373 radians per second, while for the RC circuit, it was at 1 radian per second. And indeed, at 1 radian per second, the magnitude is minus 9.6 dB, as shown by that block. I also notice that at this frequency of minus or 0.373 radians per second, that the phase angle is minus 52.1 degrees, and at 1 radian per second, it's minus 90 degrees. Now, in analysis of second-order systems, I can predict what this bandwidth is, which is the frequency at which the second-order system, the RC filter, drops minus 3 dB, in this case minus 2.99 dB, below of its low frequency value, or 0.707 of its low frequency value. And that frequency is 0.373 radians per second. Well, the way we can predict that is by taking this algebraic transfer function, just rewriting it in a more standard form where the term multiplying, or the constant multiplying s squared, is 1, and then just comparing it to our general form, which is omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Omega n is the undamped natural frequency of the system. Zeta is the damping ratio. If you compare these two forms, you can get an expression for omega n and for zeta. And then the expression for the bandwidth for a second-order system is given by this rather complicated expression. But just to show you that we can predict this, if I substitute in omega n and zeta obtained by comparing this to this, substituting into this formula, I get 0.374 over tau for my bandwidth. Tau is 1, so this is 0.374 radians per second, which is what I have here. Here's a way we can compare our analysis, our predictions, to our, again, numerical analysis, and eventually to our hardware measurements. Here I've done something similar. I've taken an RC filter, but now compared it to an RC unity gain buffer op-amp RC filter. So for the RC filter, the transfer function is the same as before, 1 over tau s plus 1. I let tau equal 1 for simplicity, and I find that minus 3 dB at a frequency of 1 radian per second, or 1 over tau, which I see here, is my bandwidth. And the RC filter drops off at minus 20 dB per decade. For the RC buffer RC, the frequency response plot is simply the result of the square of the two ideal RC low-pass filters, two in series with no loading. At high frequency, I get minus 40 dB per decade. And the frequency here at minus 3 dB is 0.64 radians per second. But I also notice that at 1 over tau, or 1 radian per second, the RC filter has an amplitude ratio of minus 3 dB. and the RC with a buffer has an amplitude ratio of minus 6.02 dB. Minus 3 dB is 0.707, minus 6 dB is 0.5. So here's just more use of MATLAB and Bodie plots to further understand the RC low-pass filter, the RC low-pass filter, and the RC buffer op-amp RC low-pass filter. One last comparison to complete the study. Here we compare an RC second order low pass filter where the downstream RC filter loads the upstream RC filter. And I compare that to the second order filter with a buffer op amp, a unity gain buffer op amp that prevents the downstream filter from loading the upstream filter. For the RC filter, this is my transfer function. For the RC buffer RC filter, this then is my transfer function. We see that at high frequency, the behavior is the same, minus 40 dB per decade slope. At low frequency, the behavior is the same. It's flat at 0 dB. The difference is where is the breakpoint? Where does it drop? Minus 3 dB. And we see for the RC buffer RC, you have a higher bandwidth than you do for the RC combination. And you can also see the frequency response phase angle plot for both the RC and the RC buffer RC. What is a passive high pass filter? Well, we simply interchange the capacitor with the resistor, and we measure the voltage out across the resistor, and we get what we call a high pass filter that's passive. The capacitor has an impedance 1 over CD. The resistor has an impedance R. If I assume I out is 0, so I'm looking to obtain the ideal output-input transfer function, I can use my voltage divider and say V out over V in is equal to R times R plus 1 over CD, which results in this expression. Again, S and D are the same. If I define tau, the time constant, to be R times C, I get this transfer function. This is the transfer function for a high pass RC or CR filter. The low pass filter only allowed signals to pass below its cutoff frequency point. The passive high pass filter circuit only passes signals above the selected cutoff point, eliminating any low frequency signals from the waveform. Here is a general plot for the frequency response of a first order high pass filter. Tau is R times C. Again, the frequency, the cutoff frequency in hertz is 1 over tau times 1 over 2 pi. And that cutoff point is the frequency at which the amplitude ratio is minus 3 dB or 0.707 of its high frequency amplitude ratio, which is 0 dB. This is the pass band. This is the stop band. Slope is plus 20 dB per decade in this region. At the break point, the phase angle is now plus 45 degrees, plus 45 degrees. The output leads the input by 45 degrees. So these are my Bodie plots, my frequency response plots. Amplitude ratio versus frequency, phase angle versus frequency. Here we see a CR high pass filter with a unity gain buffer op amp with infinite input impedance ideally, 0 output impedance ideally, gain of 1. So there is no amplification. And this is my high pass filter, and the buffer op amp prevents any loading from anything I might connect to it downstream. If I now compare a low pass filter to a high pass filter, and I pick tau, which is RC for both, to be 1, which means that 1 over tau is the breakpoint, the low pass filter drops minus 3 dB from the low frequency value of 0 dB at the breakpoint. And the high pass filter gets to minus 3 dB from the high frequency value of 0 dB at the breakpoint, which is 1 over tau, which is 1. We see that the low pass filter has a high frequency slope of minus 20 dB per decade. The high pass filter has a low frequency slope of plus 20 dB per decade. At the breakpoint, the low pass filter has a phase angle of minus 45 degrees. The high pass filter has a phase angle of plus 45 degrees. The low pass filter goes from 0 at low frequencies to minus 90 degrees at high frequencies. The high pass filter goes from plus 90 degrees at low frequencies to 0 degrees at high frequencies. Here is as we did for the first order low pass filter, if I connect two high pass filters in series, the second stage will load the first stage. And we could go and perform the same analysis that we did for the RC circuits in series. So in this case, we already know the second stage will load the first stage, and the overall transfer function will not simply be the product of the ideal high-pass filter transfer function times the ideal high-pass filter transfer function because of this loading, because I out from the upstage filter is not 0. And so we can say again in practice, cascading passive filters together to produce larger order filters is difficult to implement accurately, as the dynamic impedance of each filter order affects its neighboring network. However, to reduce the loading effect, we can make the impedance of each following stage 10 times the previous stage. So R2 would equal 10 times R1. C2 would equal 0.1 of C1. Second order and above filter networks are generally used in the feedback circuits of op amps, making what are commonly known as active filters. A bandpass filter. A bandpass filter is created by connecting in series a high-pass filter to a low-pass filter, a CR filter to an RC filter. So by cascading together a single low-pass filter circuit with a high-pass filter circuit, we can produce another type of passive filter that passes a selected range or band of frequencies that can be either narrow or wide, while attenuating all frequencies outside of this range. This new type of passive filter arrangement produces a frequency selective filter known as a bandpass filter. The width or frequency range of the filter's bandwidth can be very small and selective, or very wide and non-selective, depending upon the values of R and C used. The center, or resonant frequency point, is the geometric mean of the lower and upper cutoff points. At this center frequency, the output signal is at its maximum, and the phase shift of the output signal is the same as the input signal. Here is the frequency response of a bandpass filter. It's a general diagram. So it shows here for the high-pass filter, the breakpoint frequency, the cutoff frequency, F sub L, is shown here. It's minus 3 dB below the 0 dB level. The low-pass filter is the second stage, and the breakpoint is F sub H, and minus 3 dB at that frequency below the low frequency value of 0 dB. So in the pass band, it's approximately 0 dB. In the middle of this is where the amplitude ratio is the greatest, in this case 0 dB. It's very broad, and the phase angle is 0 degrees. The output and the input are in phase, and the amplitude ratio is the same. And that center frequency is determined by the geometric mean, which is the square root of the product of F sub L and F sub H, the cutoff frequency of the high-pass filter and the cutoff frequency of the low-pass filter. And this then is our bandpass filter. We see that the phase angle goes from plus 90 degrees to minus 90 degrees, and it's 0 degrees at the center frequency or resonant frequency, which is the geometric mean of the low and high cutoff frequencies. The slopes are as we know them to be, minus 20 dB per decade at high frequency, plus 20 dB per decade at low frequency. Here I've breadboarded a bandpass filter, a CR RC bandpass filter, and connected it to my MIDAC to determine experimentally the Bodie plot. Here is that Bodie plot. We see this is a bandpass filter. Here's my high-pass filter. Here's my low-pass filter. And in the middle, I have a bandpass filter. And again, by my choice of R, C, and R for the high pass, R and C for the low pass, I will get different plots. But you can see it goes from essentially 90 degrees at low frequency to minus 90 degrees at high frequency and 0 degrees at maximum. The amplitude ratio is a maximum. So this is the experimentally determined bandpass frequency response plots. If I now insert a buffer op amp unity gain between the high pass filter with this ideal transfer function and the low pass filter with this ideal transfer function, I know that because the low pass filter will not load the high pass filter because of the unity gain buffer op amp, the output input relationship between V out and V in will be given exactly by this relationship. Again, because there's no loading because of the buffer op amp. If I predict this in MATLAB and create the frequency response plot, where here I've picked R2C2 to be 0.1, R1C1 to be 10, you can see here that at 0 or 10 to the 0, which is 1 radian per second, I have my maximum amplitude ratio, 0 dB, and a phase angle of 0 degrees. And that is my geometric mean of 0.1 and 10. And that is my resonant frequency for this bandpass filter. And you see the slopes, minus 20 dB per decade, plus 20 dB per decade, plus 90 degrees, minus 90 degrees. I then tested this in hardware where I have a CR high pass filter and a RC low pass filter with a unity gain buffer op amp connected to my DAC in the Bodie plot configuration. And I get my Bodie plot for that hardware setup, along with the gain and phase angle, essentially as functions of frequency. Active filters. We have already created two active filters, one for our low pass filter, one for our high pass filter, to prevent any loading, where we have inserted a unity gain buffer op amp in both places with infinite input impedance, ideally, zero output impedance, ideally, no amplification. So the addition of these buffer op amps makes these two filters active filters. However, we can amplify the output by using op amps. However, there is a high frequency limitation for active filters. Here you see a typical op amp open loop frequency response. At low frequency, very high gain, but then as the frequency increases, the open loop gain decreases until at 1 megahertz in frequency, the amplitude ratio is 0 dB or 1. We call that the gain bandwidth product. So unlike a passive high-pass filter, which has in theory an infinite high-frequency response, the maximum frequency response of an active filter is limited to the gain bandwidth product, or as we see here, the op amp open loop gain. And that's the gain bandwidth product of the operational amplifier being used. Still, active filters are generally much easier to design than passive filters. They produce good performance characteristics, have very good accuracy with a steep roll-off, and have low noise when used with a good circuit design. Here is an active high-pass filter, and we show the high-frequency limitation of the open-loop amplifier bandwidth gain product. We see the open-loop frequency response of the op amp. It's 100 dB at low frequency, and then it rolls off minus 20 dB per decade until at 1 megahertz, the amplitude is 0 dB or 1. So for the high-pass filter, which has a low frequency slope of plus 20 dB per decade, and then at the breakpoint or cutoff frequency, it levels off, and ideally it would level off and increase to infinite frequency. It's limited by the op amp open loop bandwidth, and it then follows the curve for the open loop amplifier frequency response and follows this line down to 1 megahertz at 0 dB. I can create active low-pass filters with amplification by taking my passive RC low-pass filter and adding an amplification stage with a non-inverting op amp that has a gain of 1 plus R2 over R1. Similarly, I can take my passive high-pass filter, my CR filter, with this transfer function, add an amplification stage through the non-inverting op-amp with a gain of 1 plus R2 over R1 to get amplification. I can also obtain an active bandpass filter with amplification by taking my passive high-pass filter and my passive low-pass filter and adding my non-inverting op-amp stage for amplification in the middle. The quality factor of a bandpass filter tells us how narrow or wide the bandwidth of the bandpass filter is. In a bandpass filter, the overall width of the actual pass band between the upper and lower minus 3 dB corner points of the filter determines the quality factor, or Q point, of the circuit. This Q factor is a measure of how selective or unselective the bandpass filter is towards a given spread of frequencies. The lower the value of the Q factor, the wider is the bandwidth of the filter. The higher the Q factor, the narrower is the bandwidth of the filter. And the Q factor is given by the resonant frequency divided by the bandwidth. This concludes the introductory module on filters. We have talked about passive and active filters, low pass, high pass, band pass, band reject filters. With this introduction, you are now able to read the literature on the design of much higher order filters, passive and active, and the various applications of filters in engineering practice. Thank you very much for your attention.